Good morning. This is Hope Reactor. Now, let's begin today's news.
Japan refused to hide this failure. How H3 became stronger. What makes a rocket stronger? More successful launches, a more powerful engine, or something far less glamorous? A complete record of failure. On December 22, 2025, Japan's H3 launch vehicle Flight No. 8 lifted off from the Tanegashima Space Center, carrying Michibiki No. 5, a satellite designed to strengthen Japan's positioning and navigation network. The launch initially appeared to be progressing, but during the second stage, the engine's second ignition did not start normally and shut down too early. The satellite could not be delivered to its planned orbit. For a national launch system, this was not a minor setback. H3 is the successor to the HIIA. It is meant to preserve Japan's independent access to space and support science, security, navigation, exploration, and commercial missions. So after the failure, the most important question was not simply which part broke. The deeper question was, how did the danger pass through design, manufacturing, testing, inspection, and launch preparation without being stopped? At first glance, the failed second-stage burn pointed toward the engine, but the investigation moved backward through the flight data. Telemetry, pressure, temperature, acceleration, onboard video, manufacturing records, design changes, inspection plans. Engineers separated each possibility, tested competing explanations, and reconstructed the sequence second by second. The investigation concluded that the chain of failure likely began much higher in the rocket, around the payload support structure, or PSS. The PSS is the adapter that holds the satellite above the rocket's second stage. It used a lightweight sandwich structure made from carbon fiber reinforced plastic skins bonded to an aluminum honeycomb core. Investigators found that internal delamination had developed between these layers. When the payload fairing began to separate, the shock likely caused that hidden separation to spread. The structure then became unstable and failed. The satellite is believed to have detached around the time the first and second stages separated. What looked like an engine problem may therefore have been the final symptom of a structural failure that began elsewhere. This is why serious accident investigation cannot stop at the first broken component. A component may explain where the mission ended. It does not always explain where the failure began. JAXA's investigation went beyond hardware. It examined why the defect had not been found before launch. A new out-of-autoclave bonding process had been adopted to improve competitiveness. During development, manufacturing, and transport constraints led to a design change that divided the splice into 2 sections. That change made the process more complex, but the risk of local overheating between the splice areas and the possibility of internal delamination were not fully identified. The structure passed its strength test. Its external appearance showed no abnormality. Because internal delamination had not been recognized as a likely failure mode, additional non-destructive inspection after the qualification test was not included. In other words, the work was largely performed according to the approved process. The failure did not come from one person ignoring a rule. It came from a risk that the rules themselves had not been designed to catch. That difference matters. Blame asks, who made the mistake? Root cause analysis asks, why could trained people follow the process and still allow the danger to survive? Blame can close a case quickly. Root cause analysis can protect the next 10 missions. JAXA used methods that trace the event as a chain through time, identifying where that chain could have been broken. The review expanded from manufacturing into project management, risk management, knowledge sharing, technical review, and training. The conclusion was uncomfortable but valuable. The organization had rules. The inspections required by those rules were performed, but the process for identifying hidden risks, especially risks created by new technology and later design changes, was not broad enough, so the response was not limited to repairing one adapter. For important operational missions, a mechanically fastened PSS design was selected. For already manufactured hardware, damaged or questionable bonded sections were removed and repaired. The repaired structure was tested under vacuum, static loads, and shock loads. JAXA also strengthened post-qualification inspection, including non-destructive inspection, cut section inspection, and destructive testing when necessary. Experienced specialists and independent reviewers are expected to play a larger role when new technology or major changes are introduced. Lessons from the failure are also being converted into checklists, shared knowledge and training. This ensures that critical experience does not disappear when individual engineers retire or move to another project. Then came the test that mattered most. On June 12, 2026, H3 flight number 6 launched with a repaired PSS and additional sensors. The rocket followed its planned sequence and placed its payloads into the intended orbit. Sensor data showed no abnormal strain behavior in the repaired structure. That flight did not erase Flight No. 8. It did something more useful. It tested the investigation's conclusions against reality. A hypothesis was formed. A repair was designed. The structure was tested on the ground. Then it was flown. And the flight data was examined again. This is how failure becomes engineering knowledge. Spaceflight will never become risk-free. Every new material, process, and design change can create what engineers call an unknown unknown, a danger that has not yet been imagined. The strongest organization is not the one that never fails. It is the one that refuses to waste a failure, one that preserves uncomfortable data, one that separates responsibility from scapegoating, one that turns a damaged component into a better test, a stronger review, and a lesson the next generation can use. H3 Flight No. 8 did not complete its mission. That loss should not be softened or romanticized, but by exposing the chain of events, correcting the design, testing the repair, and sharing the lessons, Japan can make its path to space more reliable. A successful launch proves one flight. A failure investigated honestly may protect many flights still to come. The unknown becomes hope. This is Hope Reactor. Would you trust an organization more if it openly published its failures or less? Tell us what you think in the comments.